Calculations involving the equilibrium constant. First, let's review the equilibrium constant expression. When we're writing down the equilibrium constant expression, we're writing down the concentrations of the products on the top part, and each concentration for each product will be raised to the power of the coefficient that you have in the chemical equation. So for example, in my equation here, I have two products, product C and D, and the coefficients are C and D with a lowercase letter. So you have that in your equilibrium constant expression, you have concentration of your product C times concentration of your product D, and the concentration of C is raised to the coefficient, concentration of D is raised to the coefficient 2. So I have C, my coefficient here, that's C, and I have my coefficient here for my generic equation, and that will be the coefficient right there. Now that goes over the concentration of the reactants. So I have two reactants, reactant A and reactant B. So I have concentration of A, that's your coefficient A, and that will be the exponent for the concentration of A, and you have concentration of B, second reactant, and that will be the coefficient for B. So concentration of products over the concentration of the reactants. Another thing, when you're writing down your equilibrium constant expression, we're not including concentrations for pure liquids or solids. So we work with gases and aqueous substances. When we're trying to calculate anything involving the equilibrium constant, all of the concentrations that we're adding in that equilibrium constant expression, they have to be concentrations at equilibrium. So we have different types of calculations, okay? So specifically four of them. And I'm starting from the easiest one going all the way to more complicated calculations involving equilibrium. So remember, this is everything related to dynamic equilibrium. I'm just using equilibrium. So you have the first type of calculation is just plugging in numbers in the equilibrium constant expression to find out the value of that equilibrium constant. So this is the simplest type of calculation because you're just plugging in numbers and getting your final number for a numerical value of that equilibrium constant. So I have a generic reaction here, A2 plus B2 going to 2AB. That's the product. So the first thing that you have to do for calculations involving the equilibrium constant is writing down the equilibrium constant expression. The equilibrium constant expression, it's not something that you're going to get. You need to know how to write it down. So I'm going to write down my equilibrium constant expression. I have only one product, which is AB, and that product has a coefficient equal to 2, so that will be square, and that goes over. You have two reactants, A2 and B2, so A2, B2. The coefficient for both is just 1, so I'm not writing it down. So in the problem, what you're trying to calculate is the value of K. Okay? That's what we're trying to get. So if you want to calculate the value of K, you need concentrations at equilibrium. So the problem is telling you the concentration at equilibrium for A2, it's 0.78. Concentration at equilibrium for B2, it's 0.11. And for AB, it's 0.11. So you have all concentrations at equilibrium, which means that you can just plug in the numbers in your equation and you can get the numerical value for K. AB it's 0.11, that's still square. A2 it's 0.78 and B2 it's 0.11. So you can just calculate how much is the value of K. So I am just rounding my final number to two significant digits, and that will be the value for the equilibrium constant when the concentrations at equilibrium for the product is 0.11. For your two reactants, A2 it's 0.78 and B2 it's 0.11. For the second type of calculations that we have, you're going to be given the value of the equilibrium constant. So you actually have a numerical value, and you're going to have also some of the concentrations at equilibrium, and you're using that to find out a missing concentration. So let's check the problem. You have your reaction. In the problem, you have a numerical value for K. You are given the concentrations at equilibrium for a reactant H2, a second reactant I2, and what you're trying to calculate is the concentration at equilibrium for HI. So we have identified the information that it's given, what we're trying to calculate. So let's write down the equilibrium constant expression for this problem. You have the equation right there. Your product is HI, coefficient 2, so that will be squared. Your reactants H2, coefficient of 1, and I2, coefficient of 1. So looking at the problem, we have the number that goes here, 69. We have this number H2, we have this number here I2, and what we're trying to calculate is that number right there. So you can pause the video and you can try solving the problem. So we're trying to isolate HI. So the first thing you have to get that number. To get rid of that number, you have to multiply on this side, on both sides, by the same number. When I do that, I get 0.0262. That's equal to HI squared. So 0.062 is coming from the multiplication of 0.0195 times 0.0195 and that number times 69. Okay? So I'm getting rid of this part here by multiplying that on both sides, and I get 0.0262. So now still we don't have the concentration of HI yet, because this is the square of the concentration of HI. So to get the actual concentration, we need to use the square root to get rid of the square, and that will give you the concentration of HI. Still using three significant figures, 0.162. So for you to have an equilibrium constant with a value of 69, the concentration of H2 is 0.0195, the concentration of I2 is 0.0195, the concentration of HI, your product, is 0.162. Now we're looking at a problem that is a little bit more complicated. In this type of problem, you don't have concentrations at equilibrium. You need to find the concentrations at equilibrium from given information. So whenever that happens, we use the same approach, which is using what is known as an ICE table. An ICE table is just a method that allows us to arrange given information. So you have an ICE table when we're using initial concentrations, looking at how that concentration is changing and getting finally concentrations at equilibrium. So we have a problem right there, the composition of hydrogen sulfide. So let's check what information it's given. We have a numerical value for K, which is very important for this type of calculation. Another thing that it's given is initial concentration of hydrogen sulfide, which is the only reactant in this example. What we're trying to find is concentration at equilibrium for the two products. So we don't have any concentrations at equilibrium given. So we have to use the information that is given in the problem to find out those concentrations at equilibrium. And the information that we have, it's an initial concentration and the numerical value for the equilibrium constant. Now, the numerical value for the equilibrium constant is actually giving us a lot of information. You have 1.67 times 10 to the minus 7. That number is a very small number. Remember, if the value of K is greater than 1, it means that your equilibrium is shifted towards the product side. So at equilibrium, you have more product than reactant. If the numerical value of K is lesser than 1, then that means that at equilibrium you have a lot of reactant and a small amount of product. Your ratio is calculated concentration of products over concentration of the reactant. If you have a lot of reactant, it means that you have a super small number for the product, which is the number that you have on the top part of your ratio. That small number divided by a large number that you have for the reactants will give you a small numerical value for K. So that number right there times 10 to the minus 7, it's a small numerical value of K, which means that when the reaction is reaching equilibrium, at that point you have a small amount of product and a lot of reactant. So your reactant is not converted to product entirely. It's actually converted just by a small amount. That's what that numerical value for K is telling you. And that is going to be a very useful information. You will see why. I'm going to copy my reaction right here so we can start working with the ice table. So when we're working with an ice table, this is the arrangement that we need to follow. ICE, initial, the change, and at equilibrium. Initial means concentration, initial concentration. If you check your problem right there, you have an initial concentration for H2S. It's given. Your initial concentration for H2S is 0.1. So I'm going to write down that number right here. So what that initial concentration is telling you, you're starting this reaction with zero point 0.1, 0.100 molar for your hydrogen sulfide. Now, if you're starting your reaction with that amount for your reactant before your reactant starts being decomposing, you have nothing for your products. Remember, that's your initial concentration. You're starting with that amount. That amount is going to start decreasing to give you the products. But initially, what you have is just the reactant. Nothing has happened yet. Since nothing has happened yet, you don't have anything here. And your products, they are not formed yet. Now the change is telling you for a reactant, we're looking at the reactant first. The initial concentration of your reactant will be decreasing over time to form the products. So that initial concentration that you have right there, it's going to be decreasing over time by an amount. We don't know how much that amount is. That's what we're trying to find out. So since we don't know by how much that concentration is going to be changing, I'm going to put an X. So my initial concentration for the reactant, we know it's going to decrease over time because it's a reactant. We don't know by how much. So since we don't know an actual number, I'm using X. Now, another thing, for that hydrogen sulfide in your reaction, you have 2 moles. So in front of this change here, we're going to use the same coefficient. So your initial concentration for hydrogen sulfide is changing by minus 2x. The x represents that actual amount that your concentration is changing by. Now, on the product side, you see, the products are being formed as the reaction progresses. So as time passes by, your hydrogen sulfide is being decomposed. That initial concentration for hydrogen sulfide will be decreasing, and the concentration of your products will be increasing. Always products increasing, reactants decreasing. By how much that concentration of your products is increasing, we don't know, but the concentration of your products is being formed from the reactant. So if the reactant concentration is changing by an X amount, the concentration of your products is going to be increasing also by an X amount. You're getting the products from the reactant. Whatever amount of reactant is being used up, it's being used up to form the products. So another thing is that you have your coefficient, and we need that number in front of that change. For S2, your coefficient is just 1, so I'm not writing it down. So now let's see how we get the equilibrium concentration, which is what we're trying to find. Yeah. Your equilibrium is given by, look, your initial concentration is changing by that amount. So at equilibrium, the concentration of your hydrogen sulfide will be 0.100 minus 2x. At equilibrium, the concentration for hydrogen would be 0 plus 2x. At equilibrium, the concentration of sulfur is 0 plus x. So now we have the concentrations at equilibrium. We don't have an actual numerical value, but we know we have an idea. Okay, so my initial concentration of hydrogen sulfide is decreasing by 2x. The concentration of the hydrogen is increasing by 2x. The concentration of S is increasing by x. So I'm going to write down my equilibrium constant expression. My product over the reactant. We have this number here. That's given. Now, if you check, right, you have your equilibrium constant expression, you have concentrations at equilibrium. You don't have an actual value for them. But if we know how much is X, we can actually get a numerical value for all of the concentrations at equilibrium. Look, if you know how much is X, 0.100 minus 2 times that number will give you the concentration at equilibrium for H2S. If you know how much is X, 2 times X will give you the concentration at equilibrium for hydrogen. If we know how much is X, we can determine the concentration at equilibrium for sulfur. So we can actually calculate the numerical value for X, plugging in everything in the equilibrium constant expression. H2, it's 2x, and concentration for hydrogen is square, so I have my number right there. S2, it's x, and for that one we just have 1. For H2S, we have 0.100 minus 2x, and that will be squared. So now I have all of my concentrations at equilibrium from the ice table. I'm plugging them in my equilibrium constant expression. We can solve for x. That will give you a numerical value that we can use to actually get how much the concentrations at equilibrium are. Now, there's something that we can do to simplify the mathematical process that we need to follow to get that numerical value for x. The value of k, the numerical value of k, is 1.67 times 10 to the minus 7, a super small number. Your initial concentration for H2S is 0.100. When you have a numerical value of K that is such a small number, you have a lot of reactant, which means that your reactant is not converted to product. It is converted to product, but the amount is so small that we can actually assume that that initial concentration remains the same. When we calculate the value of x, I will show you why we're assuming this. So whenever the numerical value of k right here, whenever the numerical value of k is a number that is 10 to the minus 4, minus 5, minus 6, minus 7, keep getting smaller, right? 10 to the minus 8, minus 9, they're smaller, getting smaller as we increase that negative exponent. Your numerical value of k is getting smaller and smaller. Whenever you have a numerical value of k that is so small, like 10 to the minus 4 or smaller than that, you can actually assume that your initial concentration for the reactant is not changing, and you can simplify your problem assuming that your concentration at equilibrium for the reactant it's exactly the same as your initial concentration. Your amount of reactant, the amount of reactant that is being converted to product, it's so small that you will have a number that is very close to 0.100. We're going to get the number and then we're going to actually see that our assumption is true. If we're assuming that the initial concentration is equal to the concentration at equilibrium because the value of K is 10 to the minus 7 right there. What we're actually doing is changing this 0.100 minus 2x back to just 0.100. So we're actually erasing this term here, 0.100 squared. So simplifying that concentration at equilibrium for the reactant, you have now 2x squared times x over 0.100 squared. And all of that it's equal to 1.67 times 10 to the minus 7. So we can actually work this problem to solve for x. And you're trying to solve x because you want to know the concentration at equilibrium for H2. The concentration at equilibrium for H2 is 2x. So you actually need a numerical value of x to calculate that concentration of equilibrium for H2. We also need the concentration at equilibrium for sulfur S2. So the value for that concentration is given by x. So whenever we get that numerical value of x, we can actually find out what the problem is asking for. So let's start solving this. 2x, that will be 4x squared, times x, that will be 4x cubed. 0.100 squared, that will be 0.01. And now we have to do 1.67 times 10 to the minus 7 times. That will be 4x cubed. Divide by 4 on both sides. That will cancel the 4. And now you have x cubed. Let me get how much is that. So this is 4.175 times 10 to the minus 10. Still not the final answer. Okay? This is x cubed, and we have that x cubed is equal to 4.175 times 10 to the minus 10. So we have to get rid of the cube. You need to use cubic root of on both sides. The same thing, if you cannot find how to get the cubic root in your calculator, you can do to the power of 1/3. Okay? That will give you the same thing. So I'm getting x equals to 7.47 times 10 to the minus 4. Now, to find out how to get the cubic root, check in your calculator. It's probably a second function, and it will look like this with an x. So since it's the cubic root, you have to put 3 followed by that, and in here you're going to put your number 4.175 times 10 to the minus 10. Put that number in parentheses. If you're doing the exponent 1/3, put that exponent also in parentheses just in case. You should get the same number. So now this is the value of x. With that value of x, we can actually calculate what the problem is asking us to find out concentration at equilibrium for H2 and for S2. So concentration H2, it was 2x, right? So 2 times that number, the value of x, it's going to tell you how much is the concentration at equilibrium for H2. 1.49 times 10 to the minus 3, or 0.00149. Concentration at equilibrium for S2, it's equal to x, which is 7.47 times 10 to the minus 4. Now, we assume that your concentration at equilibrium for H2S, your hydrogen sulfide, was the same as your initial concentration, 0.1, right? In the ice table, we have 0.100 minus 2x. Okay? You can do in your calculator 0.100 minus 2 times the value of x, which is 7.47 times 10 to the minus 4. and you will see that you get a number that it's extremely close to zero point 0.1. I did it and I have 0.0985. So your initial concentration is actually changing by a small amount. And we can actually assume that at equilibrium, that concentration it will be equal to the initial concentration. You can solve the problem for x without making the assumption, but it will take longer to actually get that value of x. Another possible type of problem is when you're not given the numerical value of k and you have to find out that numerical value of k. You need to find out also concentrations at equilibrium. To calculate the numerical value of K, the equilibrium constant, you need concentrations at equilibrium. So for this type of problem, we also use the ICE table. We're not using ICE table only when you have all concentrations at equilibrium to calculate K, or you're given K some concentrations at equilibrium to find a missing concentration. For everything else, we're actually using the ICE table. Another thing, in this problem, remember in the previous example, you had a numerical value of K 1.67 times 10 to the minus 5. Minus 7. So based on that initial numerical value of K, we made some assumptions, right? Like the concentration at equilibrium is going to be equal to the initial concentration. But in this problem, we cannot make any assumptions because we don't have an actual numerical value for K. We're making the assumption based on a super small numerical value of K, which means that at equilibrium you have mostly reactant and just a small amount of product. In here, we don't have a numerical value, so we cannot make any assumptions. So let's see what we have in this problem here. You have the reaction, you have an initial concentration of the reactant methane CH4, you have one concentration at equilibrium right here. And we need to find the value for K. So let's start by writing down the value, the expression for the equilibrium constant. So K for this problem So to find that value for the equilibrium constant, we need concentration at equilibrium for one of the products, C2H2, and the reactant CH4. We do have concentration at equilibrium for H2. Okay, that's given 0.12. But with that information, we can find something else. So let's prepare the ICE table first. Initial concentration for your reactant, it's given right there in your problem. Initial concentration for the product, it's 0 because those are being formed. Now the change, reactant is decreasing by 2x, always x. The products are increasing, coefficient of 1, that will be x. Second product is increasing by x also, but now you have a coefficient right there, so that will be 3x. So here at equilibrium 0.087 minus 2x, For this product here, we have x, 0 plus x is just x. For the second product, 0 plus 3x, which is just 3x. Now, you know that the concentration at equilibrium for H2 is 0.12. So you see how I have here 3x. It's my concentration at equilibrium for H2. 3x is the same as 0.12. It's given in your problem right there. If the concentration at equilibrium using the ice table is equal to 3x, and that's equal to 0.12 because the problem is telling you at equilibrium the concentration of hydrogen is 0.12. So 3x is the same as 0.12, which means that we can actually use that information right there to find out the value of x. So it will be 0.12 divided by 3. So you see, we did a lot of work in the previous problem to find out that numerical value for x. But in this example, since we know how much is the concentration at equilibrium for H2, and using the ice table, we know that that concentration is equal to 3x. You can actually find out that value for x. And now, if you check your equilibrium constant expression, you have concentration of C2H2, which is x, and x is 0.04. Concentration of H2, we know that's 0.12. Concentration of CH4, it's 0.087 minus 2x, and we know how much is x. So we can actually calculate a numerical value for all of our concentrations here. And we can plug in the numbers in the equilibrium constant expression and get the value of K. So 0.0 minus 2 times 0.04. This one here is just 0.04. And then for hydrogen, we have 0.12. So we can plug in the numbers here. So this 0.007 is coming from 0.087 minus 2 times 0.04, which is your value for x. 0.12 is given right here in your problem. And 0.04 is just the concentration, the value of x, which is what we have at equilibrium for C2H2. So we can get the numerical value for K. That will be 0.04 times 0.12 cubed, all of that divided by 0.007 squared, and just rounding to two significant figures, I will get something close to 1.4.